Hey everybody, this is the last chapter 10 video. I'm going to work a few problems on the board just to show, just general gas problems, how we can apply the idle gas law or the combined gas law or some of the other problems. So the first two or three I'm going to do are in the PowerPoint. So in the PowerPoint, there's a slide that says practice at the top of the slide, and the problem given is shown right here. An experiment shows that 0.495 grams of a sample of an unknown gas occupies 127 milliliters at 98 degrees Celsius and 754 torrs of pressure. Calculate the molar mass of the gas. So, couple things. I mean, obviously I recognize that we're talking about a gaseous sample. The two equations I like to use, one is the ideal gas law, which is PV equals nRT. The other one is the combined gas law, P1 V1 over N1 T1 equals P2 V2 over N2 T2. Whenever I read a problem, I always try to think, can I use one of those equations to solve the problem? The way I know which one to use, if it only gives me one value for the pressure, the volume, the moles, and the temperature, typically they're going to give me 3 out of the 4. But if it only gives me one value for each variable, then I know, oh, okay, it's going to be a combined gas law, it's going to be an ideal gas law problem. Now, if in the problem they describe like an initial pressure and a final pressure, or an initial temperature and a final temperature, or something like that, where I know they have one condition in the beginning, but then they change something. If that happens, then that's where I'm going to use the combined gas law, where I have P1 and P2 and V1 and V2 and so on. Okay, and remember with that equation, sometimes you can eliminate anything that's not changing. You can just erase those things from the equation and use whatever's left over. Okay, so the problem I described, they gave me a volume of 127 milliliters. They gave me a temperature of 98 degrees. They gave me a pressure of 754 torrs. Okay, and then they gave me a mass, 4.495 grams, but in the ideal gas law and the combined gas law, mass doesn't fit into that directly. And then finally, they want me to find the molar mass. Okay, so when I see one pressure, one volume, one temperature, it makes me want to do PV equals nRT. And if I can plug in a pressure, but in the ideal gas law, the units have to be perfect. The pressure has to be in atmospheres. The volume needs to be in liters. N is moles, T is temperature. So if they gave me P, V, and T, I know R is a constant. All I had to do is plug everything in and I can figure out the moles of the gas. So I'm going to go ahead and do that. My pressure tells me the pressure was 754 torrs. So I'm going to have to convert that real quick. Pressure is going to be 754 torrs. But then you have to remember the conversion from torrs or millimeters of mercury into atmospheres is 760 millimeters of mercury is what the pressure of 1 atmosphere will give on a barometer. So that's what we're talking about here. So my conversion is going to be 1 ATM. That's normal atmospheric pressure, gives 760 torrs or millimeters of mercury. So I just divide by 760. Do that on my calculator real quick. 754 divided by 760 equals, that's going to be 0.992 atmospheres. That's my pressure I'm going to plug in for P. 0.992 ATM. My volume. Well, the problem gave me 127 milliliters. I can just divide by 1,000. That's going to be 0.127 liters. N is my unknown. I don't know what N is. It's not the answer to the question, but it's going to help me get there. Okay. R is going to be 0.0821 liters atmospheres per mole Kelvin. And then my temperature gave me 98 degrees Celsius. I have to add 273. That's going to give me 371 Kelvin. So there's my setup. I'm going to solve for N. So it'll be 0.992 times 0.127 divided by 0.0821 and 371. and I got is 0.00414 moles. So that's my moles. Now the question wants the molar mass. So the molar mass of a compound is how much a mole of the compound weighs. We should know, and this is going to come up in 1211, but in 1212 it comes up in a lot of problems. The molar mass is the grams of a compound per mole. So the units are the grams of the compound over the moles. Grams per mole. Like I know that water has a molar mass of 18 grams per mole. It'd be 36 grams per 2 moles. Or 54 grams per 3 moles, right? It's always that ratio of 18:1 for water. So basically for the molar mass, they gave me in the problem, they told me the sample weighed 0.495 grams. So I could plug that on top, 0.495. And then we found out that in that sample, there's 0.00414 moles. So 0.00414. So I can just divide 0.495 divided by 0.00414 equals, and I got about 119.6 grams per mole. So that is the molecular weight of this gas that was being described in this problem. Okay, so that's our first problem. Now let's go to the next one that's right under it. Says, what's the density of nitrogen gas at 1 atmosphere and 100 degrees Celsius? So what we're talking about here, it's a pure sample of nitrogen gas. They told me the pressure is 1 atmosphere. The temperature is 100 degrees Celsius, but I'm going to go ahead and convert that to Kelvin. It's going to be add 273. It's going to be 373 Kelvin. And then they asked me for the density. Now, what units are used for density? It doesn't specify in the problem. We'll give a little bit of leeway here, but if you had a solid or a liquid, the density is usually given in grams per milliliter. Like the density of water is 1 gram per milliliter. The density of aluminum is like 2.7 grams per milliliter. Okay, so those are normal numbers for solids and liquids. Gases, though, have a much smaller density. So actually, most of the time when you do density of a gas, it's going to be in grams per liter. Okay, instead of grams per milliliter, it's going to be grams per liter. So on your final exam or the 4th test, chances are they're going to specify the units, even though this problem didn't. So we're going to go ahead and solve for the problem. We're going to use the units of grams per liter because that's the common unit for density of gases. So what am I going to do? Well, again, this problem I'm looking at, I have 1 pressure, I have 1 temperature. It's not talking about any of the changing conditions kind of thing. So I'm not going to use the combined gas law. I'm going to use the ideal gas law again. Okay? With the ideal gas law, P equals nRT. There are a couple different ways you could approach this problem. Okay? The easiest one is it says what's the density of nitrogen gas at 1 atmosphere and 100 liters, 100 degrees Celsius. It doesn't tell me how much gas I have, and really the density is like the amount in it, like it's the grams per liter or whatever. So I need to make up a volume to say, okay, well, let's just pretend we had 10 liters of this gas, and let's figure out what the density is, because what happens is I know the pressure, I know the temperature, I know R, but there are still 2 values that I don't know. And if I don't know those 2 values, I only have 1 equation here, I can't solve it. So I'm going to just go ahead and lock in and say, okay, let's just assume that I have 10 liters. Okay? And then, because the volume and the moles, they're going to be proportional to each other somehow. And as long as both of them are unknown, I can't do anything with that. But if I just lock one of them in, then that's going to allow me to solve the problem. Okay, so now let's plug everything in. So I got 1 atmosphere, 10 liters, N is my unknown, R is 0.0821 liters, atmospheres per mole Kelvin, and then temperature is going to be 373. So again, I'll grab my calculator. So I'm going to have on the left side a 10, then divide by the 0.0821 and divide by the 373. So N should be 0.32, I'm going to call it 65 moles. And if you remember, the question told us it was nitrogen gas, which is N2. Okay, so I'm solving for density, and I know I need to have the grams of nitrogen gas over the liters. Well, if I have moles, all I have to do is convert moles to grams, and then that's going to go in the numerator there. So, 0.3265 times the molecular weight of N2 is going to be about 28. So that's going to be, if I do 1 mole, 28 grams. That's going to give me 9.14 grams of nitrogen. Okay, and I'm actually going to rewrite my grams per liter. I'm going to write it as a true fraction. Grams on top, liters on the bottom. I'm going to put the 9.14 on top. That's how many grams of nitrogen I have. And then we locked in the volume at 10 liters. So if I do 9.14 divided by 10, that's going to be 0.914 grams per liter. That's the answer to the problem. Okay? So we'll do one more of these. I think we have time for quick. So the last one on the slide, this is one that's an actual reaction. Water decomposing to H2 and O2. Okay, so they say what volume of oxygen at 754 torrs and 40 degrees Celsius does a decomposition of 2.33 grams of water produce? So I'm starting with 2.33 grams of water, and I want to finish with the liters of O2. Okay, now if you remember your mole map, if you look back to the end of chapter 4, I gave you a mole map that actually showed the gas calculations at the on both sides, to where we're going to start with the grams of the reactant, that's grams of A, and when we get to the end, we get to the volume of B if it's a gas. Okay, and to get from one side to the other side is always going to be a 3-step process for us. The first step, changing grams to moles, we divide by the molecular weight, which for water is 18. It's been a while since we've done these calculations, so it's kind of good to review this stuff because the final is coming up in after the 4th test, or the 5th test. So, first step changes me to moles of water. Second step, I need to switch out from water to oxygen. That's going to be my 2-to-1 ratio. The one I'm starting with goes to the bottom. So it's going to be 2 moles of H2O to 1 mole of O2. So grams cancel grams, moles of water cancel moles of water. So now I have moles of O2. Now this is going to be where when I have the moles of the oxygen and it's a gas, I want to get to the volume. The third step is going to be PV equals nRT, where whatever answer I have up to this point, that's going to be the moles of oxygen. So whatever I get right there is going to plug in as N. And then they gave me the pressure and they gave me the temperature. I know R, I can plug all that in and solve for V. V is going to be my answer. Okay, so I'm going to have to step out of that little area to work. So let me calculate my moles of oxygen I got from the first 2 steps. It's going to be 2.33 divided by 18 and also divided by 2. So the moles of oxygen I got is 0.0647. That's N for my P equals nRT. Okay, I got that from the first two steps of the calculation. Then my pressure, again at 754 torrs, which a few minutes ago we figured out that was 0.992 atmospheres. So I'm going to start putting everything. My P equals nRT is going to be 0.992 atmospheres. My volume is what I'm solving for. R is 0.0821. Oh, I skipped. N, I do everything in order, is going to be my 0.0647. R is 0.0821. And then the temperature is 40 degrees Celsius. 273 plus 40 is 313. So now I can work that out. And I got the volume of the gas is going to be 1.68 liters when I solve for V. So, hope all that helps. That's the end of our video series. You guys have a great day.